Well, hello and welcome back to Engineering 201 Electrical Fundamentals, and we're going to be looking at experiment number 4, which is hopefully a demonstration of Thevenin's theorem. So with that, let's go ahead and get started. I'm going to switch camera views on you, and we'll get into looking at the circuit and so forth. So we'll hop over here. This may be a little hard to read, but you'll have this in hard copy at your disposal. Like I said, laboratory number 4. And this is one that has a pre-lab. You've got the Thevenin equivalent circuit as seen by resistor 6. So what you're going to want to do is take this circuit here, and when it says it's seen by resistor 6, you'll want to remove that resistor 6. You'll take that resistor 6 out and then figure out what the Thevenin model is. So that would include finding your open circuit voltage across here and then the Thevenin equivalent resistance. And we'll talk in a moment about how to calculate that. But I would encourage you to really calculate that. When we were used to meet students face to face and whatnot, this was a time in lab when some people came prepared with the pre-lab, but some people weren't prepared and they really had to sit down and grind through it, and it was a real learning experience for them. So I encourage you to stop at this point and make sure that happens. Well, let me talk a little bit about how you can do that calculation. So I've got the same circuit here. Like I mentioned before, get this all in the camera here. There we go. So you're going to take the circuit. I think mesh analysis is probably a good technique with this. So I'll assume this is I1. I will assume this is I2. And then because we've opened this, we've taken that resistor 6 out of there. This is open and has no current. So we could say by inspection that has no current. Likewise, if there's no current in here, then your voltage drop across this resistor, V is equal to IR. The current is equal to 0, so we have whatever the resistance value is times 0. That gives you 0 voltage. So essentially then the voltage from this point here up to this point here is your V open circuit. Okay, and I've put this in formula here. So you could say that your V naught or your V open circuit is going to be V2, whatever this source is, plus I1 times R4. So this current here, I1 times R4. So the voltage across there plus the voltage across there gives you your V open circuit. So with that, I would encourage you to stop and to figure that out. Then the second part of it comes to finding out what your Thevenin resistance is, or the equivalent resistance. And you can actually, on this one, you can use the shortcut because we don't have any dependent sources, we don't have any of those diamonds. We can use the shortcut on this. And if it does have a diamond, I'd refer you to the class lectures. It's more involved, and you can use the more involved way on this. The shortcut is just that. It's a lot easier. So the shortcut says that we short out these voltage sources, and we're going to do this on the circuit. We're not going to leave this source in here and short it out. That's a good way to start a fire. But we'll take this source out. We'll short this out. We'll take this source out. We'll short that out. And then we look back into here and figure out what the equivalent resistance is. So again, you're just going to short this out, short that out, look back into these terminals without the R6. R6 is not there. So look back into those terminals and now figure out the equivalent resistance for this. So those are two things that you will need. You'll need to come up with your Thevenin voltage, and you need to come up with your Thevenin resistance. So I would encourage you at this point to pause the video or to stop the video and to get out a piece of scratch paper and to hammer that out and to do that, because that's really important. One, for this lab so that you know what you're looking for, and two, so that you have those skills. So stop the video and do that. Well, I'm assuming that you're back with us. You've got your voltage open circuit, your R Thevenin. This circuit actually is a different circuit for us in some regards, that it has two sources. It's the first circuit that we've dealt with two sources. This V1 here, this is 9 volts, and this is 5 volts. And if you look at the lab station that I have, it has two sources, and it has a variable source, so that would work for the 9 volts, and it has a 5 volts, so that would work for this. The only problem is those two sources are contained within the instrument, and their ground, their negative, is hooked together. Well, if we look at this then, this point here, this negative, is certainly not at the same potential as that. This resistor, this R3 right there, exists between those. So if I wanted to do this, I'd either have to find another source, which is actually what I did, or I could have modified the experiment, changed permanently the experiment and got rid of that resistor there. I opted to keep the experiment the same for consistency's sake and go find another source. So I'll talk a little bit about that. So what we're going to do here is hopefully then, with our equivalent or our Thevenin resistance, one and the same, and our open circuit voltage or our Thevenin voltage, again, one and the same, we're going to build this greatly simplified circuit, and we'll be able to put resistors in here, whatever R6 is, 1K, 2K, put it in there and see how this thing behaves. Okay, and these are essentially the steps that we're going to go through to do this. So construct circuit number 1, that's the complicated one with the two sources, and measure the output voltage. Remove R6 from the circuit and measure V open circuit. That should be pretty close to what you calculated for your V open circuit. Replace R6 with a 2K. So up here we have a 1K, and then we've got a 2K here, and measure V naught. So just so that we make sure that this is not an anomaly, that we're showing some consistency. So we've got 3 measurements there. Then it says to remove both power supplies from the circuit and replace them with wires. So this is where we're shorting out the sources, so to speak. We don't want to actually short the sources out. We'll take the sources out, and then we short the spots that were left there by them. And I'll talk about this more. So when I measure the equivalent resistance, that's going to give us R Thevenin. And finally then, we're going to construct circuit number 2. That's this circuit that we were just looking at, with our V open circuit and our R equivalent, and put the resistors in here. You'll see measure V naught with R6 of 1K ohm and 2K ohm. Okay, so that's what we're doing. There's one other slight complexity here. Probably if you found this, you found that this R equivalent is not a nice round number in terms of a resistor that I might have. And with COVID and kind of operating on a shoestring here in my office, so what do? Well, I opted to tune a potentiometer to that particular value. So let's see what that looks like. So there's the circuit there, R Thevenin, V Thevenin. How can I deal with this resistor maybe not being a standard value? Well, I put the potentiometer in there. Going back to experiment 1, remember I get a variable resistor if I use the center lead, so this will be the center lead, and one of the outside leads. This one here will just not be connected to anything. So then I adjust this to the resistance I want, and presto, I've got the resistor there. So that's what we will do. Lastly, the questions that you're going to be working through, the question sheet, and again, you'll have this in hard copy form. Show your calculations and results for V open circuit and R Thevenin. Okay, so again, take that scratch paper that you paused the video, did it on scratch paper, and you can put it down here. And you can use the stated values for the resistors, or you can use the measured values for the resistors. I'll give you that data also. So that's going to be important so we know what we're shooting for. how do your measured values and your how do your measured values compare, presumably, to these? So you've got your calculated values. How do your measured values compare to those? Hopefully fairly close, because we'd like to say that Thevenin's equivalent works. From a perspective of the terminals at V0, that's the output terminals there. Remember when we had this, there's our terminals, the V0. What are the differences between circuit 1 and circuit 2? And use your lab calculations to support your answer. So I'm not going to say much on that. I don't want to spoil the surprise, but when we get done, that should be a pretty easy question to answer. So let's get going with that then. I'll set this out of the way here. And I'm going to move the camera right here. And it's probably going to be a little far away to really see everything, but I wanted to give you a little better idea of what's going on here. Again, on my trainer, it has ground here. That's a ground lug. It's black, so it's a little bit hard to see on the black background. And then it's got a minus voltage. We'll be using that next time for our op-amp experiment. It's got a positive voltage, and that's what I'm going to tune to that 9 volts. Okay, so this will be the 9 volts. And there was the 5 volts, and on face value, you might think that, well, hey, you could use that 5 volts, but again, this terminal here is not at the same potential there, and these are at the same potential inside this board, so they're not too independent. They have the same ground state. So what I've done then is I've just got a second one over here, and it's kind of off the screen, but basically it's exactly the same as this one. It's just sitting over here, and I'm using the ground lug here, and it's, wouldn't even know, it's just off the screen, but the 5 volt lug. So the 5 volt lug like that. There's one over here, and then I've got these wires. I don't know if you can see that one. This wire here, that's my +5, and this is the ground. Okay, so I've taken care of that. That's going to be my 5 volt source, and then my 9 volt source is coming from here. So there's the ground, and I'm using this bus bar there coming down to here, and that's the ground, so that's that point right there. And then the plus voltage, that's right there. There's plus, and that's coming over to there. And again, I've tried to arrange these a lot like they are on paper. So we have this resistor here, that's R1, this resistor there, that's R2. You know, I didn't put a piece of wire in there for that, but I just jumpered R3 over to here. And let's see, we've got R4 right there. There's R5, and then R6. I have these resistors out. This one over here, I've got a little note to myself so I don't mix them up. This is the 2K ohm one. This is the 1K ohm one. This actually measures out 0.982K. The 2K measures out 1.99K. And I will share all of that data with you. So in past labs, I spent quite a bit of time talking about measuring the resistance and whatnot. I've measured the resistance already. These are well within spec. The only thing that I might say is, do this, is one, we want to measure the resistance with the voltage off. The voltage is off on this thing. And if I just try and, for instance, on this R1 right here, if I want to try and measure the resistance of this thing, I'm going to get the resistance of the entire circuit, which is not what I want. So I want to unhook at least one end of it. So I'll just move that out of the way. There we go. And then I can measure this resistance right there. So 2.00. Okay, which is good. I think before, yeah, 2.00 is what I'd measured before. So it's supposed to be a 2K, so that's great. So I'm not going to do that for each one, but just a quick recap. Do it with the power off, and you have to unhook at least one end so that you don't measure the equivalent resistance. I'm not going to belabor it again. We've got bigger things to think about here, although that's certainly important. Well, with that, let me go ahead and power this up. And I'll have to power this other one up, so I should have my sources then. Let's make sure that that works out. So if I measure the voltage across here, turning that to volts, hopefully you can see that. Try to twist that a little bit. Okay, so I've got DC volts, so I measure from there to there, and 4.99. Okay, so that's pretty close to 5 volts. I'm going to jot that down. 4.99 volts. And then for this one, right here, that should be the 9 volts, right? So I measure from there to there, and 8.99. 8.99. So 8.99 volts. I've got that recorded. I'm going to turn this, double check these connections. Okay, so we should be good. So now I want to come over here, and I've got these leads coming out over so I know where this point is. But it's probably going to actually be easier for me to measure the voltage right here. This is open. Okay, so it's open. So if I measure from there to there, I've got 6.59, 6.59. Okay, so that's with it open. 6.59 volts. With it open again, we said that the current through this resistor should be 0. So that means the voltage across it should be 0. Well, let's test that out. So I'll measure the voltage across there. And yeah, it's 0. I could put it down into millivolts and see if I get something. But that's just kind of a side, so I'll just leave it at that. So then what I want to do is turn the power off on this thing. And I want to put my 1K resistor across there. Power back up. And I should be able to get the voltage now with this 1K. So it'll be the voltage from there to there. 2.39. Well, 2.39. And power down. Pull this resistor out of the way and swing the 2K resistor into place. Power back up. Now this resistor, it's just hanging, this end is here. If this is high voltage, you get shocked on that end probably, so I'd want to be careful with that, but that's probably not a big concern in this, this lab. It's certainly not affecting the results though. Okay, so when I measure the voltage across there, 3.539, I'm going to call that 3.54. 3.54. Okay, so I think that's all of the voltages that I needed to measure. I might run back here just real quick and with this one out, double check that everything is remaining remaining the same. That is that this should have been pretty close to 5. Yep. And that this should have been pretty close to 9. Yep. Good. Okay. So we've got then we've measured the open circuit voltage across here. With this open, we showed that the voltage across there was 0, so the current through there is 0. And then we had a 2K resistor across here and a 1K resistor across here. So now I'm going to take these sources out. So this is my 5-volt source. I'm going to remove that. I won't need that again. And the 9-volt source, I will unhook that, okay? Because I don't want to short out. I don't want to short out those sources. That's like opening up your car hood and putting a piece of steel across the battery terminals. That's not going to end well for anything. And then I think what it says is once you've taken those sources out, to short across these, so I'll take a yellow wire and short across that on where the 9-volt source was. So I've shorted that out right there. And then where the 4-volt was, I have put a green wire there. I'll short that out. So there's the short where the 4-volt source was. Here's a short where the 9-volt source was. And then I just look back into these terminals on this thing, set the resistance, and those that have done the calculation, hopefully everyone's done the calculation, they have some idea what this should read. Now, I'm not going to put my probe right there just because it's a little bit harder to get that. It'll be the same value right there, assuming there's no resistance in this wire. So I'll measure that, and I get 1.72 k ohms. 1.72 k ohms. Okay, 1.72. I'll check that again because that's a key piece of our experiment here. Maybe I'll run back over to here. So instead of measuring there, right there's a resistor. I can put the lead on, and instead of measuring here, I'm going to put it on there. And that's just a matter of where these wires go in. It's hard to get contact. So I'll come back here where the lead is not insulated, and I can get contact better. 1.719, 1.72. I'll stick with that 1.72 k ohms. So good. We've got that. So now our task is to build this circuit right here. Okay, so let's do that. The way that's going to work is I have my positive voltage here. It's coming over here. It's going down on this one. So that's the positive voltage. And then I need to get this resistor. So I'm going to use this 10K pot, and I'm going to go in on the middle terminal. I've got that work for you here. We've got this. There's the positive going to the middle terminal, and one of the outside terminals is going this way. So let's make that happen. So there is this. That's jumping to the middle terminal here. And this is built into this, so if you look down here, and it's pretty hard to see. Work very well. Let me just grab the camera, see how well this works. And yeah, here we go. Try not to make people seasick, but this is, come on, focus right there. Okay, so this is the diagram that we have here, where I've got several pins that'll connect to the middle, and then on the outside are pins that connect to either lead. Come on, focus, you darn thing. Okay, so that's what we're building it as. Okay, so we come in here to the middle. So that's where we're coming from, the positive lead to the middle of this. And then we come from the outside, and that goes up to here. So that comes from the outside up to here. So that's this point right there. And then the ground side, that's the ground here, is coming through here, down to here. And then I have this wire jumping right there. So that is over here. So then really at this point, and I don't have R6 on here. I'm going to come over and grab these in a little bit. But really this point right here is this point, and this point right there is that point. Okay, I'll go ahead and zoom in here a little bit since I've got a little bit of an angle, but you can see that better again. And I was zoomed out there earlier because I wanted to show you that I had two sources going on this thing, but we don't need the two sources anymore. So we have this point right here, that's that point, and this point right here, that's that point. So let me go back out just a little more so you can see the multimeter. Okay. That doesn't show up very well. There we go. Okay. Okay, so a couple of things that need to happen here. I need to get the resistance tuned. So let me hook this up, and I will unhook this side here. So that's open, so I can just measure from here to here. I'll pull this wire out just a little bit. See what we've got there. 1.78. So I'm going to try and adjust it just a little bit. What did we say we wanted? 1.72. I think if you did your calculations, you got about 1.75. So I think, in fact, I'll leave it right there. Our calculation showed 1.75. Our measured from this other circuit showed 1.72. So, and this is pretty touchy. I've got it here at 1.735, 1.74. I think I'll leave that like that. So 1.74. Jot that down. And then for V open circuit, we needed to tune that to what? 6.59. So that's the next step. Let me do that. Put this on volts. Turn this on. And could really put this back in here. So I'll measure now from there to there. And we've got 8.99. That must be left over from when we had 9. So I'll turn this down. What do we want? 6.59. Okay, and I think if you did the calculations, you probably came up with 6.625, something like that. Let me double check that for you. 6.625, yeah. So we measured 6.59. So there's 6.6. Let's see if I can get a little less. That's pretty touchy, so. Okay, so there's 6.59. I think I'll leave it like that. You could say, well, we could go to 6.625. Yeah, but as you saw on that knob, it's pretty touchy, so I think we're there. Okay, make sure those are making good contact. So these are my output terminals now. So let me measure that, okay? That is the output of this circuit right there. So this should be the same as V open circuit. So I should get that 6.6, 6.59, and I do, okay? So with no resistance in there, I've got the same voltage, 6.59. And then I'll turn this off real quick. If I put the 1K in here. Fire this up. So with the 1K, I have 2.38. 2.38 volts, and I think on the other circuit we were 2.39, so that's boding well, looking good. And then the 2K, put that in there, fire this up. I'll measure across there, 3.527, let's call that 3.53. 3.53, and those of you following along, I think you recognize the previous circuit was 3.54, so again, pretty close there. So that's good. Let me check my points here. We did the new circuit with 1 ohm, 1K ohm, and 2K ohms. I think we are good with that. So let's check the questions real quick. So our questions, show your calculations. You got to be able to do that. How do your measured values compare? I think that's going to be a pretty good thing. And then from the perspective of the V0, what's the difference between circuit 1 and circuit 2? Well, that should be a fairly easy answer also. So I think we've got you set up for that. I will get the data to you so you know the value of all these resistors and whatnot, and you can base your calculations on those if you want, although they were pretty close. So if you just take these stated values, you should be in pretty good shape. I might mention a few things here. Let me switch views on you. Go back so that you know I'm still here in person. The lab's a little bit frustrating, probably, that you're not getting to move the components and whatnot, but probably to some extent a lot easier to write up because you're not trying to write a lab up with maybe data that's not very good and whatnot. Hopefully I'm giving you good data. If we think about what you're needing to learn and whatnot, if you're following along in the labs, if you're pausing and making the calculations, if you're also maybe pausing and saying that, why did he make that measurement? Pause and think about that, and would I have made that same measurement and whatnot? I think you're really fully engaging in the labs. If you're a civil engineer, you're probably going to be doing just fine. In fact, this class, with a civil engineer, if you learn some node analysis and mesh analysis, those are very similar to analyzing fluid systems, piping systems. If you think of friction loss of fluid in pipes and pumps raising the potential, very much like an electrical circuit. So knowing those analysis techniques, node and mesh, and having some general ideas of how electrical measurements are done, if you leave this class with that as a civil engineer, you're probably going to be in pretty good shape. The electricals and the mechanicals, we're going to be at this for another term and try and figure out what next term looks like. But they might want to do a little bit more on their own. I did grab, and let me pop over out of screen for a second and grab a couple things. Sorry about that to disappear on you. And I think I will switch back to the other camera here. But you don't really necessarily need all this equipment to do some experiments. I know people have asked, well, you know, can we have kits and do the experiments at home? I was nervous to do that because I think people would tend to probably make mistakes and burn up their kit. And that's important learning, but then how do you finish up the experiment if you've burnt up your kit? But at some point, certainly the electricals and maybe even the mechanicals may want to go out on their own and do some things. And you don't necessarily need to have the best equipment. This is actually the school's fluke meter, and this thing is about $500. This is a nice meter. You can see the leads here. They actually have clamps on the end of the leads. Just the leads on this thing are about $100. So really high-end, nice tool. And when we're in lab face-to-face, and hopefully we get back to lab face-to-face, I bring this in now and then so you can get some exposure to a tool like this and recognize that. But this meter, and this is what I've been doing our labs with. This is a fluke, and I guess I should put the numbers out here in case you become super wealthy over Christmas break or something. This is a Fluke 87, and it has true RMS, and that's going to be a big deal when we talk next term. But Fluke 87, that's a great meter. It's a standard. But this meter, 15B or 15B plus, I just checked this morning, and you can get it for somewhere between about $90 and $110. So for a Fluke meter, that's actually really good. But just to, and I bought several of these for the school. I've bought 2 or 3 of them for my personal use. They're kind of my go-to meter. It's a good compromise between really expensive and something that you can actually take out to the field, and if it gets stolen or falls off a building or something, it doesn't super ruin your day. So 15B, that's what I would go buy again. But you know, $100, you're a student. I recognize that that's expensive. So you could, if you wanted to. And I looked this up. This is actually not a bad little meter. I've got several of these. You can get these at Harbor Freight. I think right now they're $6.49. If you start to measure really small values of resistance and whatnot, this is probably not going to be my go-to meter, but I actually keep one of these in the toolbox of each car, and so if I need to do some troubleshooting or whatnot, it's there. If it gets stolen, you know, no big deal. If I step on it, no big deal. If it sits for 3 years and the battery corrodes, no big deal. Sometimes even Harbor Freight will have a deal. If you buy some other stuff, you can get one of these for free. So that's a low budget item, and that's one of probably really the only tools that you might need. So then how do you do your experiments? So some of you that are thinking, well, Thanksgiving's coming up, Christmas is going to come up. What do I want to do with the rest of my time? And I realize you're busy this term, so this is something in the future. But I just hopped on Amazon, and here is a electric playground 50-in-1 experiments. Okay, I had one of these when I was a kid. Not this exact one. I think mine was, you know, the nice 101 experiment one. But here's 50-in-1. The only reason I picked this is it was one of the cheaper ones, so $17.99. So, and they have all different types, but if you want to do some hands-on stuff, get one of these, build all 50 of them, play with them, and then start to modify them and whatnot. And if you're worried about, you know, burning the thing up, you're only going to burn up $18. So with this and with that Harbor Freight meter right here, so you got this for $17.99. You got this Harbor Freight meter. You can really do a lot of exploring and figuring out in the electrical area. So some of you that are wanting to do, maybe I'll finish up face-to-face here. Some of you that are wanting to do more hands-on things and whatnot, that might be an option for you to do a little more work over the upcoming break. And speaking of the break, it's really going to come on us pretty fast as we go into November. We've got Veterans Day, we've got Thanksgiving. You come back from Thanksgiving and the term wraps up very, very fast. So I caution you with that. And also, if you want to do some more hands-on work and whatnot, there are ways for you to do that on the cheap. So with that, I will leave you be. I'll make sure that you get the data so you can finish up this lab, and hope the term is going well. I hope this class is going well and your other classes are going well. And, thank you for listening. Take care till next time.